Welcome all of you, and let's start with the new chapter, that is electromagnetism. So electromagnetism is basically a chapter that will be discussing about the bridge between electricity and magnetism. But before that, I would love to discuss the concept of magnetic field that you have already done in class 9th, since we'll be applying here in the chapter. First of all, we need to understand what is a magnetic field. The space around a magnet in which the needle of a compass rests in a direction other than the geographic north-south direction is called magnetic field of the magnet. So on the screen, you must be viewing a red and a blue structure, right? A rectangular structure where I have written N and S, and I hope so you understand what I have drawn here. This is representing magnet. Red represents north and blue represents south, right? And magnetic field, as we just defined, that it's a space around the magnet where we can feel the presence of a magnet, where we can see it might be attraction or repulsion because of the other material that is in the vicinity of the magnet, right? So what about magnetic field line? A magnetic field line is a continuous curve in a magnetic field such that tangent at any point of it gives you the direction of the magnetic field of that point. So let's discuss about the properties of a magnetic field. Magnetic field lines, they are closed and continuous curves. They are just like a stretched rubber band. It's just like, if you remember, we have done this, isn't it? We even plotted in the practical in class 9. So these are representing your magnetic field lines, right? And as we know, they run from north towards south. So it is from north to south they are running outside magnet. But when we talk about inside magnet, they run from south to north. So these are the two properties, that they are continuous closed curves and they behave just like a stretched rubber band, right? So closed continuous curve, and second is they just like stretched rubber band, right? And the third is the two magnetic field lines, they never cross each other. If you see here, these are not intersecting. They are not intersecting like this, right? Suppose this is one magnetic field line and this is the second magnetic field lines. They are not going to cross each other. Why is it so? Why they can't cross each other? For that, we need to understand that at every point on the magnetic field line, all these points just very close by, right? So I'm just taking the points that are far away. These points at the magnetic field lines are actually giving you the direction of the magnetic field. So how to find out the direction of magnetic field? You need to simply draw a tangent of this curve, right? So when we draw a tangent to the curve, we get the direction of the magnetic field. And now if you see here, if I consider these two magnetic field lines and if I assume that they cross each other, then what will happen? This point is common to this and this field line, right? So according to this is also giving me magnetic field and this is also giving me, because I've drawn the tangent to the two curves, right? So these two are actually giving me the direction of magnetic field line of the point that is existing on curve A and on curve B. But the thing is, if you see here, isn't it, it's just like a case when a person is moving in two different directions at the same point. Or I can say a person is present at different places at the same time, which is not possible, right? A person can't move in two different directions at the same point. This is not possible, right? So that's why our assumption that the two magnetic field lines can intersect each other is not valid, right? So the two magnetic field lines, they never cross each other, right? Cross each other. And next is, now if you see here, the maximum strength of the magnet is near the pole, and pole is somewhere here. Let me mark it with the, right. It is not exactly at the extreme points. So the maximum strength of the magnet is near the pole, right? So we assume that the magnetic field lines are going to exist in a cluster near these ends. And if you see, there is a difference between the magnetic field lines, and if we move away from this magnet, they will become almost parallel to each other. They will just become parallel to each other like this, right? These magnetic field lines. So actually, these parallel lines, they represent uniform magnetic field, right? And the cluster near, this cluster near the magnet, it actually tells you that the strength of the magnet is maximum near, right? So we again draw a conclusion that if the magnetic field lines are very close by, it indicates the strength of the magnet is maximum there. And if the magnetic lines are going to be parallel like this, it represents a uniform magnetic field lines, right? So now let's start with electromagnetism. So it was long time back, around 1820, a person named Hans Christian Orested was there. He was a Danish chemist and physicist. He was a teacher also, and once he was performing an experiment in his class, and to his astonishment, he saw a very peculiar behavior of the electric current that was passing through the circuit. So what happened? He was actually performing a practical in which current was supposed to be passed through the circuit. When he observed a nearby magnetic compass, it was deflecting. So he was aware that magnetic compass can give deflection only when some magnetic field is existing nearby, right? So it was a big surprise for him. So he thought the only magnetic field that can exist now must be because of the current flowing through the conductor. So he started working on it and he performed various experiments. So this is the setup for Oysters' experiment on magnetic effect of current. When he was working on the circuit, it was a rheostat was connected to a battery and key was open here, right? So we can write here key. So it was open here. So that magnetic compass was lying nearby, right? And it was not deflecting since key was open. And the moment he closed the key, so the key was closed. And immediately this deflection, it started moving towards this side. So it was like this way, right? It started this way. So it was your north and it was south. So why it was not giving any deflection? Because that time the magnetic compass was only acting under Earth's magnetic field. And we know that a magnet always aligns itself in north-south direction, right? So magnetic compass was giving them deflection in north-south direction. Now when key was closed, now this wire, this conductor is now has started acting as a magnet on passing current through it, right? So now the magnetic compass is under the effect of the magnet, that is due to this current carrying wire, and the magnetic field of the earth. That's why there was deflection of this magnetic compass now in this direction, right? So what he thought, that let me see what is going to happen if I change the direction of current. So what he did, he simply changed the terminals, right? He simply changed the terminals, and to his surprise, now this became negative and this became plus. And to his surprise, this thing that was north was giving deflection in your west and this east, northwest and southeast. Now the deflection simply became opposite. So how it started acting? Now it was like this way. North became this side and south came to this side, right? It started deflecting this way. That is just opposite to the deflection that was happening before, right? So what he concluded? He concluded that the magnetic compass is giving deflection only when current is passing through it. It means the current carrying conductor is acting as a magnetic as long as current is passing through it. Second, it will not give any deflection if circuit is open, since that time the magnetic compass is giving you direction that is north-south under the effect of Earth's magnetic field. Third, the deflection become opposite if the terminals are changed. It means the direction of current has changed. That's why the poles also become opposite, right? And next he saw that when you keep the magnetic needle on the wire and below the wire, the polarity, it just becomes opposite. Why is it so? You know what? You can use your thumb and finger. Suppose you are keeping magnetic compass like this, right? Now, it is giving direction in this part. When you are going to make it opposite, isn't it? It was this side, now it is becoming this side, right? Now, if it is, this is your magnetic compass. This is the magnetic compass. I have to turn it like this to keep it. I can't make it this and this, because otherwise the metallic part will come in the upward direction, right? So if you keep it this way and then when you turn it this way, right, what will happen? They will just attain opposite direction. So this is how Orested, he made few conclusions regarding the magnetic effect of the current. So we discovered few more points. So what all were those points? Let's see. Now let's talk about magnetic field and field lines due to current in a straight wire. So it is just in continuation with Oysters' experiment, you can say. So now we are going to find out how a current carrying conductor is going to behave like a magnet, and what about the magnetic field lines, how they are going to develop. So for that we are just going to make a circuit diagram. So this is, suppose a conductor, a wire is there. So here you have a battery, right? And this is open, so no magnetic field is there. But if you close the circuit and when current is going to pass through this, magnetic field lines, they will start developing, right? Now wire itself, now it has started behaving like a magnet, that current carrying conductor, right? This wire. But since this wire is acting as a magnet, but it itself is not having any polarity, right? Now the magnetic field lines, as we know, they run from north to south direction. But as such, you can see from here, we are not able to find out which direction is north and which is south. So to clarify for this, how to have north pole and south pole, we have a right hand thumb rule. So what is right hand thumb rule? According to right hand thumb rule, you need to hold a current carrying conductor in your right hand. Now the thumb points in the direction of current, so the encircling fingers will give you the direction of the magnetic field, right? It means from this direction to this direction, magnetic field lines are running, fine? So this is your right hand thumb rule. I again tell you, according to right hand thumb rule, if you hold a conductor in your right hand such that the current is flowing, in the upward direction, then the encircling fingers will give you the direction of the magnetic field lines this way. Now suppose I just take a current carrying conductor such that it is in downward direction. So what is going to happen? When it is in the downward direction, no doubt magnetic field lines are going to there, right? It is in downward. So they are going to move this way, right? So it means now they are going to move this way. So this is for the magnetic field lines, how these magnetic field lines are produced by a current carrying conductor. And otherwise also we can even verify this in our laboratory. We can perform an experiment. So we are going to have the same setup. Now on this wire, we are simply going to connect, we are going to have a cardboard, right? Now this cardboard, you just sprinkle iron filings on it. Iron filings. I hope you understand iron filings. We have done experiments related to magnetic field lines in class 9. So what will happen when current will, now suppose no current is flowing. When no current is flowing, they will be just randomly placed here. They will be just placed randomly. But once you close the circuit, when current will start passing through this conductor, what will happen? Slowly and slowly, these magnetic field lines, they will start arranging themselves in a fixed pattern, right? So they are going to be like this. They are going to be like this. In the form of concentric circles, they will be arranging. Now, which is North Pole and which is South Pole? As I already told you, it depends upon your right hand thumb rule, right? This is right hand thumb rule, and according to this, your thumb points in the direction of current, right? And the encircling fingers gives you the direction of magnetic field. So I hope so you have followed this right hand thumb rule. So now let's proceed with, so again, just to make you clear, I have again drawn the diagram for right hand thumb rule. See, if the current is moving in upward direction, then how it is going to behave. So it will start behaving like a magnet, right? So we are going to have these concentric circles, right? Means the magnetic field lines. And how they are going to behave? Again, you put your, this is your right hand thumb rule. You hold the conductor in your right hand such that thumbs points in the direction of current. Then the encircling fingers gives you the direction of current, right? And same way, if current is moving in downward direction, again it's going to behave like a magnet, this current carrying conductor, right? Again magnetic field lines are there, right? So how they are going to behave? Again, it is moving in downward direction. So these are your encircling fingers. I'll be holding it like this, right? So current is in downward direction, so your encircling fingers, this way they are going to move, right? It means these magnetic field lines are running from north to south. So this is how you represent for the direction of magnetic field lines.